So very quickly, just to remind ourselves where we are, just zip through the past few lectures. We're talking about the Legendre symbol, n modulo p, which indicates whether or not n is a quadratic residue. So the kind of basic background problem is, given an n, given a p, coming up with nice, efficient ways to evaluate this symbol and to understand what's going on about it. The +1 indicates it's a quadratic residue, -1 indicates it's not. Our first result about this, first major result about this was Euler's criteria. Okay. Which gave us a nice way to relate the value of the Legendre symbol, +1 for a residue, -1 for a non-residue, to relate it to saying that it's congruent to this power of n. And the exponent is really nice. The exponent is half the size of the group. The multiplicative group of congruence classes modulo p has size p-1. There's p-1 elements in it. And we raise n to that power, and that gives us ±1. And it's the same ±1 as the Legendre symbol. This came from Fermat's little theorem. Fermat's little theorem tells us that any element m from the group raised to the power p-1 is congruent to 1. So when you raise something to the power of p-1 over 2, it's going to be congruent to a square root of 1, which is either +1 or -1. And it turns out that the residues will give you +1 and the non-residues will give you -1. That's the kind of starting off point for our further results about evaluating the Legendre symbol. And it ultimately leads, just hammering this result, concentrating on it, squeezing it, get as much of it out of it as you can, eventually leads to the quadratic reciprocity principle. So we took that general result, and if you look at it in a few simple cases, such as the case when you've got n equals -1, you get this nice result about the Legendre symbol on -1 modulo p. And it's based on p modulo 4. You get a similar nice result for, say, the Legendre symbol 2 modulo p. That turns out to be based on p modulo 8. There's another one, which is an exercise later on. We did it last week, which is 3 modulo p to be the next natural one to look at. And that was based on the status of p modulo 12. So in specific cases, Euler's criterion gives you these nice classification results for the value of the Legendre symbol. Okay, we could spend forever looking at particular examples of it. We want to proceed more generally, though, to reach some general facts. So we proved this other result, which we attributed to Gauss, theorem 8.7. This related the Legendre symbol as power of -1. Okay, power of -1, of course, is going to come out as +1 and -1. And the index we put on it is this number m. This is what we proved last time. So still reviewing previous presentations. What we're doing here in this result due to Gauss is you've got your n, you've got your p. You look at half of the multiples of n. You multiply n by everything from 1 up to p-1 over 2. So these multiples of n, it's half the elements from the group. The first half of the elements from the group. 1, 2, 3, 4, 5, up as far as p-1 over 2. First half of congruence class. You're multiplying them all by n, and you're looking at all these residues. And this number n is the count of the number of these which represent congruence classes in the second half of congruence classes. From p+1 over 2 up as far as p-1. And the number of those that you encounter when you look at these multiples of n, that count is this number n. And that gives you the index on the exponent on the -1. So if n turns out to be even, you're looking at a residue. N is a residue. If n turns out to be odd, means the n you're looking at is a non-residue. So we proved that last time. We worked through some examples with that last time. There's examples. There's some of the exercise problems in the end of chapter exercises ask you to apply this to various n and various p. You can actually look at all these multiples, do the counting yourself to obtain this number m, and confirm that it gives you the right result about being a residue and so on. So that's more or less then a quick trip through everything up to where we were at the end of last time. Any questions on that, or any further clarification I could give on any of that from what you were looking at it? So m is when you look at all these multiples of n is the count of the number of them which end up in the second batch of congruence classes. Congruence classes represented by p plus 1 over 2, that small remainder, all the way up as far as p minus 1. We laid it out on the board last time. You have the first half, 1, 2, 3, 4, 5, 6, all the way up as far as the midpoint. And then the second half is from the next one, just after the midpoint, up to the end, p minus 1. And these multiples of n will land in, some of them will land in the first half, some of them will land in the second half. And m is just the count of the number of them that do land in the second half. So this, you can, one way to consider this result is as a method for evaluating the Legendre result. Given a particular n, given a particular p, and that comes up in one of the questions in the exercises. It gives you some n, it gives you some p. Apply this result. You look at all these multiples, you reduce them, get the standard representative, and you look at how many of them are past the midway point. Then you, whether that's odd or even, tells you whether that's plus or minus 1. That's one way to look at it as an evaluation tool. Another way to look at it is, this is still general. We're still talking about any n, any odd prime p. So to take it further, now what we've done now is we've reduced the residue status into this number n. The residue status of n is embodied, or it's determined by this m. And it's determined by the parity of m. Parity meaning whether it's odd or even. Okay. We're not really that interested in the actual value of m, whether it's 1,000 or whether it's 2. We're interested in whether it's 1,000 or 1,001, just whether it's odd or even. That's all that affects whether this thing will come out as plus or minus 1. So that points to the next result. If we want to understand the residue status of n, okay, we want to understand this number m, we've identified here. We don't care about what value it has, what actual value it has. We just care about whether it's odd or even. Because that will say whether this power of minus 1 is coming out as plus 1 or minus 1. So does that seem reasonable to everybody? I don't really care. If I'm just interested in evaluating the Legendre symbol, I only need to know whether m is odd or even. That means that I'm only interested in it modulo 2. So this is our next result. Okay, it looks a bit scary, complicated formula, but the nature of the result is we're examining m modulo 2. So we're coming up with some kind of a involved formula, which is just going to tell us whether m is 0 or 1 modulo 2. If m is an even number, it's going to come out as 0 modulo 2. If it comes out as 1 modulo 2, it's an odd number. Okay. So knowing whether m is even or odd is the same as knowing the congruence class of m modulo 2. So this result is coming up with a formula for calculating m modulo 2. Okay. Now, there's a bit of notation here to set up the notation that's used in this result. And we've got this square bracket and curly bracket notation. Square brackets don't really have any kind of fixed notational meaning in general mathematics. They're just used for various things, just bracketing terms. Curly brackets tend to suggest that most often used for set notation, set of elements, and the elements are inside the curly brackets. However, this is new notational meaning for square brackets and curly brackets, just specific to this context of number theory. So square brackets is what's called the floor of a real number. The floor of a real number is the largest integer that's less than x. curly brackets represent what's called the fractional part. Fractional part, or sorry, floor, or it's also called the integer part. So square bracket x is the floor of x, or the integer part of x. It's the biggest integer less than x, and the curly brackets of x is the fractional part of the real number, which is always between greater than or equal to 0, but strictly less than 1. And it's the extra bit that's needed for x that isn't included in the floor of x.
Is the floor?
Yeah.
That would be 1 less than x.
No. So x is any real number. X is a real number now. So this is one of the few cases where, let's say we're dealing with a positive real number. It's one of the few cases where we go back to talking about real numbers in number theory. Actually, it'll just be, the x is actually, it'll only be rational numbers that we're considering, but it applies equally to real numbers. So let's say we're dealing with a positive real number, so it's bigger than 0, so it's over there somewhere. Somewhere before it is the last integer. So you got integers, 1, 2, 3. Somewhere before x is the biggest integer that's less than x. It's a pretty straightforward concept once you see what it is.
Yeah.
So floor of, well, not 1 less than, it's just the last integer before x. I mean, x could, if x is actually an integer, then the floor of x is equal to x. The fractional part is this extra little distance here. So this distance here is the fractional part of x. So we always have that the number x is its integer part plus its fractional part. So example, here's a rational number 40.96. If x is that, then the floor of x is 40, and the fractional part is 0.96. It's that kind of simple idea. The integer part of it and the non-integer part. Some books use this kind of adapted notation for floor. That's called the floor of x. We also talk about sometimes this number up here. So what do you think the number, the next integer after x is called? This one is the floor of x. Then the blue one must be called the ceiling of x. Oh, that's what it's called. So this is the floor of x. The other one is the ceiling of x. Blue one. I should have written that in blue.
What the notation?
Well, what do you think the notation is? This normal square bracket is what we're going to use for the floor. Other books use this one for the floor.
Maybe just opposite to
the opposite, yeah. So the ceiling is written like this. Square brackets, but without the bit at the bottom. So in other books, you may see this for the floor, or integer part, and this. Of course, this thing is always, well, if x is not an integer, these things are, this is this plus 1.
So in that case, would the ceiling be 41?
Exactly, yeah. Ceiling of x, ceiling of this x is 41. Of course, if x is an integer, the floor of x is equal to x. The last integer less than or equal to x is x itself, if x happens to be an integer. Okay, we won't dwell too long on that. It's just a piece of notation. It's not. It is this simple. X is 40.9. The integer part is 40. Fractional part is 0.9. Okay. This notation is introduced because we use it here in the statement of this result. So let's just look at what this result is. It's giving us a formula for the congruence class of M. modulo 2. This will say whether n is odd or even, so then we'll know whether the Legendre symbol is plus or minus 1. Because the Legendre symbol is minus 1 to the power of this n. Okay, it's a detailed formula. What kind of formula is it? It's a formula depending on n and p. There's two parameters in the formula, n and p. There's also a j, but that's the summation index. We're summing over j. So there's n and p in there, and there's p minus 1 over 2 in there as the upper limit of the sum. So familiar ingredients there. Now the full-blown version of the formula looks like that. But it has a simpler expression when n is an odd number. Because when n is an odd number, you see this multiple of n minus 1 here. So when n is odd, this factor here will be an even factor. So modulo 2, this second term in the sum will just be 0. So when n is an odd number, the formula is going to simplify to just this first part. So this is really the interesting part. And, yes?
I don't understand what you meant by if n is odd, that would be 0.
Because, well, so it wouldn't be the integer 0. But if n is odd, this number here would be an even number. Yeah, there's one less than n. But we're considering it modulo 2. And modulo 2, an even number is 0.
Oh, so yeah.
So what's the thing featuring in this result? It's the floor of j times n over p. So we've got this fixed number n over p, and we're looking at various multiples of it, and then taking the floor of it. Now this relates to a geometric idea, which we're going to see come up in the final, the last putting together of all the arguments for the proof of quadratic reciprocity. So we've got a line going through the origin. We think of this line as having slope n over p. Slope n over p. So this is a kind of a geometrical picture to kind of represent geometrically some of the elements of this formula. If this line has slope n over p, and j is an integer along here, so if we think of these blue points are the integer lattice. Lattice refers to this two-dimensional structure of discrete points in the plane. So the integer lattice, specifically, it's the set of all two-dimensional points where both of the coordinates are integers. Yeah, so the plane is every point in the plane. Any real number is coordinates. The integer lattice is just the set of all the points which have integer coordinates. So underneath this line, so here will be x coordinate j, thinking of j as an integer. And above it will be the point with coordinates j1. This point will have coordinates j, 2, j, 3. And there'll be a certain number of integer lattice points underneath the line. And if you think about it, that number is the floor of jn over p. The number, the count, the number of those integer lattice points there. Why? Because what's the y coordinate of this point which lies exactly on the line? The x coordinate of this line is j. The line is slope n over p. The actual y coordinate of this actual point is j times n over p. Now, in general, that's not going to be an integer. It'll just be some rational number, j times n. But the floor of this will be the last integer before that. So that will be the y coordinate of the last lattice point you meet before you land in the line. Okay. Now, okay, it's a bit mysterious why, a second ago we were talking about Legendre symbols and point elements being quadratic residues or not. Now we're looking at a diagram of a line and integer points in the plane. It's a bit of a mystery what the connection between the two is, but after we've proved this result, you'll begin to see, well, there must be some nice connection there between the two. Really, I think it's just that the elements of this argument we're giving for the proof and giving in the lead up to quadratic reciprocity are referring to these kind of combinatorial ideas. It's to do with counting the numbers of points and so on. And the diagram which appears in the proof, the final proof of quadratic reciprocity, is just one of these diagrams with a certain line through it, and the proof is about how to count the number of points in the diagram in a certain way. Which is a very kind of, in mathematics we term that kind of thing combinatorics, really, or kind of discrete mathematical combinatorical argument. Okay, so this is how to think geometrically about this expression which appears in the result we're about to prove. Okay, so let's get to it. Let's dive into it. So again, just remember what it is we're doing. We're getting a formula for m modulo 2. That will tell us whether m is odd or even. And m is the exponent of -1 in that expression for the Legendre symbol. So -1 to some power. We just need to know whether the power is odd or even to know whether it comes out as plus or -1. Okay, so we this is very much a proof by, well, we kind of just aim for the given formula. So we examine this quantity j times n over p, which is appearing here. Now, just like what I wrote down on my paper a second ago, the meaning of this notation is you can have x, the rational number x is equal to the floor of x plus the fractional part of x, integer part of x plus the fractional part. Well, here is just that expression applied to the rational number j times n over p. So some rational number is equal to its integer part plus its fractional part. So we've got a p over here. We don't like to really talk about rational numbers all the time, so I multiply both sides by p. Just take this p over here and move it to the other side. So I'm multiplying both sides by p. And now if you think about it, I'm looking at the integer j times n. I'm seeing it as some multiple of p plus a remainder bit. And the remainder bit is the fractional part of jn divided by p times p. When you look at this integer in total here, jn's an integer, this is integer times integer, so this must be an integer. So this fractional part here, what kind of range of values could this take? Well, it's something that the fractional part here is between 0 and 1, and it's multiplied by p. So this part here is between 0 and p. The fractional part is strictly less than 1, so that means this product part here, p times the fractional part, that's strictly less than p. So here we've got a large integer. It's some integer multiple of p plus a remainder bit, which is between 0 and p. So in other words, this is very familiar to us. This is integer division of j times n by p. We write the large integer jn as some number of times p plus a remainder term, is p times fractional part, and the remainder term is between 0 and p. So this is very familiar to us. It is integer division of jn times p. That's what I said there in that statement. So this p times fractional part of jn over p, this is actually, we can label this as rj. It's the residue rj. So this is the notation that we used in the previous result. Remember, we looked at each of these multiples of n, j times n, and we associated that with some residue, rj. Goes up. Another way to express the remainder is the original number, jn, minus whatever the quotient is times p. It's just another way of looking at the remainder term that comes out after integer division. It's the original number minus the quotient times the number you were dividing by. So rj we can express as jn minus p times the floor of jn over p. So, connecting with the previous proof, we've got our residues rj. So remember, these are the residues representing the congruence classes of j times n. Okay. We represented these as plus or minus times the standard residues 1 up to p minus 1 over 2. These residues rj here, remember this thing, they could either come from the first half of residues or the second half of residues. The first half of the congruence classes or the second half. If they came from the second half, we flipped them back and represented them by the negative of something in the first half. So we introduced these plus and minus signs, epsilon j. So we have that the elements of this set are congruent to the elements of this set, modulo p. Now, to start to work towards the result, you see the result has the summation of all these integer parts. So we'll get at that, we'll construct that by adding up all the remainder terms rj. Okay, so we're going to add all these numbers together, r1 plus r2, etc., up to rj. We can break apart this sum as adding up all the j's which have a positive sign attached to them, epsilon j. So there'll be some of these numbers here which have positive signs attached to them. Those are packaged into this first summation here. The other numbers from this set, which have a negative sign attached to them, well, we re-negative them, so to speak. So the ones that have a negative epsilon sign attached to them, they are, as residues rj, actually equal to p minus j. And then we work with this formula here. So the residue rj that we have there, our previous expression for that was j times n minus p times the floor of jn over p. It's quite technical, this proof. So we substitute that in. So we substitute rj for this expression here. And what's going, so this first summation remains the same. The second summation, well, we break it apart. You see, we keep on adding p. Keep on adding p all the time. And this is where the m comes in. Because how many terms are in this sum? Well, this sum just counts the j where the sign epsilon j is minus 1. That's exactly that number m, which was in the previous result by Gauss. It's the count of the number of residues from the multiples of n that ended up in the second half. So how many times are we adding p here? We're adding it m times. So we get this multiple m times p. So taking out all these p's, just the same thing, added up each time, and it's m times p. Then we're left with this minus minus times the sum of the remaining j. Next step is, okay, we got p's floating around on both sides, so to factorize out this p here. So so this is the sum of differences. So we split it into the difference of the sums, and the p's we factorize out in front. Okay. And this n, the n is a common factor in the sum of these first terms, so we factorize out the n as well. So this is good. You know, we're kind of drilling down into this idea of the sum of all the residues. We're seeing the presence of our number m, which we want to identify, modulo 2. So it's all good. And now, well, you see, there's a lot of you can spot a lot of similarity. Here we have the sum of all the j's, from 1 up to p minus 1 over 2. Here we have the sum of some of the j's which had a positive sign attached to them. And we're subtracting the sum of all the j's which had a negative sign attached to them. So here we got the sum of all the j's on the left, the sum of some of the j's minus the sum of the other j's. So it's a lot of those.
Can you not cancel P, the first equation, P into Jn over P? So the first equation on top of it.
Cancel those p's?
Yeah.
Well, no, because this one's inside the floor sign. So it's not available. I mean, if the floor sign wasn't there, yeah, for sure. But this isn't the number Jn over P, it's the largest integer less than Jn over P. We can't do the bracket because the P can't get to that P because there's a bracket in the way. So this is the largest integer less than Jn over P. So it's not exactly Jn over P. But the thing to do is to factorize it out. So that P there we bring out. The P will, I mean, it looks like we're building up a formula with a lot of elements. However, remember, the goal we're seeking is a formula modulo 2. So the fact we've got a lot of elements here, we're not too worried about it because we're going to end up reducing the whole thing modulo 2. And remember, P is an odd number. P is an odd prime. So modulo 2, P will just become 1. So the P will disappear and simplifies just the number 1 after we reduce it. So we're okay with dealing with it at the moment. Okay. So we got the sum of all the j's on the left. Got the sum of some of the j's minus the sum of the rest of the j's. Well, so we want to reconcile all that and do some kind of cancellation. So obviously we can express the sum of all the j's as the sum of the j's which have a positive sign attached to them plus the sum of the j's which have a negative sign. The j's, some of them have plus signs, some of them have minus signs associated with them. So you add up all the j's with a plus sign, you add up all the j's which have a minus sign, and then you got all the j's. So we have this equation, and now we add these two equations. So this equation here we just introduced, and this one here, we add them, and you can see the reason we're adding them. The reason we're adding them is to cancel these terms here. This one has a minus sign, this one's a plus sign. So that will get cancelled, and this one will be added to that. We'll just get 2 times this sum. 2 times something is very easy to deal with modulo 2 because 2 times anything is always 0 modulo 2. So that will just disappear when we reduce it modulo 2. So this is what we get when we add those two equations. Let's get them all, 3 of them on the screen. Get rid of that floaty bar. Sorry. Go away, floaty bar. There it's gone. So this equation added to this equation, those two summations cancel out, so they're not there. We get twice this summation, 2 times that summation. We still got our MP. And this summation is the same as that summation. So instead of n times it, we've got n plus 1 times it. Okay.
But why do you have choice? That's so cool.
Sorry?
Why do you have choice? That's true.
Because I'm adding these two equations. So it's here and it's here. When you add the two right-hand sides, you get 2 times that summation.
So sure, instead of n plus 1, should it be 2n?
No, because it's n times the summation there, but it's just 1 times the summation here.
So it's the same as.
So this is n times x, and this is x. So you're adding them, you get n plus 1
yeah,
times
yeah.
x. Yeah. Yeah. And this minus p times this summation is unaffected. That's still there. So you're adding the two left-hand sides, adding the two right-hand sides. Now this is where we hit everything modulo 2. All of this has been an equation amongst integers. Now we reduce it modulo 2. And we do the simplification. So what is this? 2 times this. What's that modulo 2? Well, it doesn't matter what the this is. It's 2 times it. So modulo 2, it's 0. Things simple. When you modulo 2, everything is 0 or 1. 0 if it's even, 1 if it's odd. So it's really, really simple modulo 2. So this summation disappears. See, the m times p becomes n. Why is that? Just remember, in all of this discussion, p is an odd prime number. So it's an odd number. So modulo 2, this p just becomes a 1. So it's an odd number, modulo 2. So this is simply m on the right-hand side. So this is really good. We were trying to get to a formula for m. So here's m. On the left-hand side, okay, this p here again becomes 1. So this summation just survives as it is. Modulo 2, we don't reduce, we don't change the representation of that. This p becomes 1. That p doesn't become a 1 because it's trapped inside the floor sign. It's not sitting there exposed as an integer p. It's inside. It's an argument to a function. This p is sitting there exposed as an integer p, so that becomes 1.
Why didn't you do that? No, it's a p squared minus 1.
Well, p squared minus 1 over 8, that's the formula for this arithmetic sum.
But isn't that going to disappear? Isn't going to cancel? It's 0 at the numerator.
Yeah, but it's if it was just that integer p squared minus 1, modulo 2, that would be 0, because it's odd number minus 1. But it's not. It's divided by 8, so you don't know if this is an odd number or an even number. So that's why this integer here has to survive.
So why not substitute for 1 again? In that second transition.
Because, so when you reduce modulo 2, anywhere that you see a p exposed as an integer, so just sitting in the formula representing the integer p on its own.
So, you mean it's nothing?
That it's not an argument to something else.
Where this is.
Just let me complete the sentence. When you see those p's exposed like that, the two places here and here, modulo 2, they become 1. So this p transforms into a 1, so it's just m. And this p transforms into a 1, so it's just this summation. This p doesn't disappear because it's an argument to this function, to the floor function. So it doesn't get reduced modulo 2. It's the value of this that gets reduced modulo 2. But we don't have a we don't know what its value is. It's represented there. So we just keep the same representation for that modulo 2. Here, we apply the arithmetic series summation formula. So this becomes p squared minus 1 over 8. Okay, I'm skipping over the details of that, but adding up all the integers between some lower limit and some upper limit, we've got a straightforward arithmetic sum formula for that. So we apply that there, and then, well, this is just a little fix, an adjustment to match the previous formula. For some reason, we prefer n minus 1 rather than n plus 1. The point is they're congruent to one another modulo 2. So equally well, the result could have been presented in terms of n plus 1, but I think it must just be customary or traditional to present it n minus 1. So this is the final result that was in the formula. In the special case where n is an odd number, because this is modulo 2, when n is odd, this factor is even, so this is 0. So it just reduces to m is equal to this summation of integer parts. So this sets us up for our proof of quadratic reciprocity. Because this notion of the quadratic part of a multiple j times this fixed value n over p, this kind of leaps out as some geometrical object. N over p refers to a line through the origin, slope n over p, and jn, the floor of jn over p is the number of integer points lying above integer coordinate j that's underneath the line. And this gives the clue to our final presentation of final kind of putting together of everything for the proof of quadratic reciprocity, which is just going to be a counting argument around this diagram in figure 8.1 a couple of pages later on. Here are the black dots of the integer lattice, and it's an extremely appealing idea, almost a weirdly simple looking idea, of we're just going to count all the integer points in this rectangle. Now, everybody knows counting points in a rectangle, you just multiply the width by the height, the size of the rectangle, the number of points in it. We're also going to count it as the number of points below the line and above the line. And that relates to the Legendre symbol. Okay? Because that result about m, remember, was the number of integer points below the line at a certain horizontal coordinate. So we're going to count all of these points lying beneath this certain line. The slope of the line is p over q. That indicates the reciprocity between p and q, a point with x coordinate p, y coordinate q, that kind of embodies p-ness and q-ness in itself. So this line is kind of somehow embodies both the prime p and the prime q. So counting the points either side of the line will somehow give us the reciprocity of p to q. Well, that'll be our last kind of final proof in the notes, which we'll do next time. It'll wrap together all the results we've seen now about the Legendre symbol, and we'll finally be able to declare that we have proved that quadratic reciprocity result. So all the results we've done on it, by using it in this factorized, flip, reduced method for evaluating Legendre symbols, that will then be fully justified, okay? Because we'll improve the last missing link, which is the quadratic reciprocity. And I spoke to some of you about in the tutorial about this last time, but I'll discuss it in the next lecture as well. These interesting applications of quadratic reciprocity to prove certain cases of Dirichlet's theorem, which basically says that every arithmetic sequence, which isn't obviously all composite numbers, every other arithmetic sequence contains an infinite number of prime numbers. We'll be able to prove some special cases of that using quadratic reciprocity. So you can have a look at that final exercise there, which is problem 3. There's quite an introduction to it. We'll deal with some of the cases of it in our next examples class. Okay, thanks for listening. We'll pick it up next time.